Welcome to our channel once again. Today we shall be discussing on how to calculate the back angle of a turning of a aircraft. A jet engine aircraft at 10 km altitude, cruising at a speed of 100 meters per second. The aircraft weighs 30 kilonewton, has a wing surface area of 100 meters squared, and its drag equation equals CD equals 0.016 plus 0.044 CL squared. Now calculate the maximum bank angle in the steady turn at 7 kilonewton thrust, while its turn is limited by thrust. Now let's pull out the parameters. We have our altitude, which is given 10 kilometer, and that's 10,000 meters. Now we have the velocity 100 meters per second. We have the weight 30 kilonewton, which is 30,000 newton. We have the wing area S, which equals 100 meters squared. We have the thrust of the aircraft 7 kilonewton, which equals 7,000. Don't let us forget, we are asked to find the maximum back angle at the altitude of 10 kilometer. So we have to find the sigma at this of the altitude, which equals 20 minus 10 over 20 plus 10, which gives us 0.3, which we will multiply by the density at the sea level. Don't let us forget, our density at sea level equals 1.225 kilogram per meter cube. Now we are asked to find the back angle, and we know that cos phi, which is a back angle, equals 1 over load factor. So our back angle is related to load factor. Now let's input our parameters into our equation. We have on the steady drag, on the steady thrust, drag equals thrust. So when the aircraft is turning at the back angle, the thrust will always be equal to the drag of the aircraft. So we have our thrust equals drag, which is half rho SV squared CD. So therefore our CD is equals 0.16 plus 0.044 CL squared. Now that's equation 2. So we substitute equation 2 in 1. That gives us drag, which equals thrust, equals half rho SV squared into bracket 0.016 plus 0.044 CL squared. Now we know that the coefficient of lift equals the load over half rho SV squared. Now let's substitute this equation in 2.5. So that gives us our drag equals thrust, which equals half rho V squared S into bracket 0.016 plus half rho V squared S multiplied by 0.44 L squared over half rho V squared L squared, all in bracket in square. So that gives us our drag, which equals to thrust, which is half rho SV squared into bracket 0.16 plus 0.44 L squared over half rho V squared. Don't let us forget, at the altitude, which the drag equals to thrust, our load factor equals our lift equals load factor times weight. So therefore let's substitute this into our equation. That gives us our drag equals thrust equals half rho SV squared into bracket 0.0016 plus 0.04 Ln, which is the load factor, multiplied by the weight, all into square over half rho SV squared. So that gives us our load factor N. We pull it out onto the other side. So that gives us the square root of thrust minus half rho SV squared times 0.0016 over 0.44 W squared, which is the weight, times half rho SV squared. From there, we have our load equals the square root of all the parameters we have. We have our thrust, which is 7,000 times half times the density at sea level multiplied by the sigma times 100, which is the wing area, multiplied by the velocity, multiplied by our constant on the coefficient of drag, multiplied by half times 1.225 multiplied by 0.3 times 100 squared, all over 0.44 times 30,000 squared. 30,000 squared is the weight of the craft. From there, we have our load factor, which gives us the square root of 4060 times 0.0046. N, which is load factor, gives us 4.3216. From there, we can find the bank angle, which is phi. So cos phi equals 1 over load factor. So cos phi equals 1.4362. Our phi, which equals arc tan 1 over 4.62. So the back angle gives us 76.6. So the angle of the aircraft when it's turning at 10 kilometer altitude will be 76.6 degrees. Thank you.